You're watching The New Stack Makers, a podcast for people who develop, deploy, and manage at-scale software. For more information and articles about at-scale technologies, please visit thenewstack.io. Now enjoy the show. Hey everyone, welcome to a new episode of The New Stack Makers. I am back with my co-host, Adrian Cockcroft. Hello, Adrian. How are you?
I'm doing fine, thanks.
Great. And Sunil Mallya. And Sunil and Adrian worked at Amazon Web Services for many years. Sunil, as I understand, you have a little bit of a background in machine learning and AI. You were head of Amazon Comprehend, the AWS NLP service, and you were also a principal deep learning scientist for ML Lab at AWS DeepRacer, where I'm sure you and Adrian had lots of fun.
Indeed. Thanks, Alex. Thanks, Adrian.
Excellent. So we were just chatting about the Nvidia conference coming up. And Adrian, you've been doing a little bit of research, and Sunil's like deep into this world. Tell me again about what is it, this chip that they've been developing over the past year or two. And maybe you all can just talk about where it is right now. And then we're going to do a demo, because Sunil's now the founder of a company called Flip AI, where they are applying generative AI technologies to debugging. So let's just get into the discussion on NVIDIA's GPT conference. Adrian, what were you saying before?
Well, every year there's some kind of big announcement, what's the next generation? And last year at GTC, the big announcement was this new GH200 architecture. So they've got the H, which is the Hopper chip, the GPU chip, the H100 everyone's been using for a while. And they've added a CPU to it called Grace. So that's the Grace Hopper, and the 200 is sort of an extended combination of the two. You put them together, and what this does that I think is interesting, it kind of flips the architecture. Before, you'd have a whole bunch of CPUs, you'd network them together, and you'd stick GPUs on as an attached I/O processor on the GPU, over a PCI bus or something. That's kind of the way most people think about how you set up systems, right? You've got your CPU-based fabric, and then you attach GPUs to it. What GH200 does is it flips that. It says, no, the GPU is the thing that needs to do most of the communication. So we're putting that as the center. And we're going to connect all the GPUs together. And the CPUs are sort of dangling off at the side if you need to talk to something else. So they're sort of I/O, or if you want to talk to outside the cluster. What that does is it lets you, what they've got is a 900 gigabyte per second, almost a terabyte per second interface on every GPU called NVLink that connects directly to all the other GPUs. And it's a coherent memory interface, so it's shared memory. And it basically means that up to 256 GPUs form a single system that you could boot one. If you wanted to, you could boot one operating system across this. Right? It's not lots of machines talking to each other. It's one huge system, which has its own fun and games for trying to work out how to program it. But it means that up to this 256 GPU limit, instead of buying a network of GPUs and machines, you're basically just saying, well, I want my machine to be this big. You just you're connecting everything together into one kind of clump. And then all the GPUs can access all the memory in all the other GPUs, and then out into the main memory that the CPUs have too. So you have high bandwidth memory on the GPUs, you have sort of regular memory on the CPUs. And this is kind of the new architecture. Was Alex still there? So that was announced last year, and it started shipping now. And so there were talks about it. A few people have their hands on it. And then sort of Sunil was saying, well, yeah, it doesn't quite work yet. So maybe let's go over this. So this is a cool new architecture. Obviously, there's a lot of debugging to get it working. So where are we in terms of this being a real thing, Sunil?
Yeah, again, I'll talk through my friends and my network. It seems like not a lot of people actually have switched beyond A100s and H100s. They're still king. The Grace Hopper, while exciting and all of these things, it's just been the firmware and the interfaces have just not been there to make a clean switch between the chips. So on the on the training side, I've barely heard anyone like actually switching. I'm sure there are developers suffering and pulling their hair out and trying to get this working, but it's not been a smooth journey. So much so that I've been offered very lucrative deals to switch over from my cluster of the 800 workhorses to GH200 by some of these providers. But I've politely refused to take on those challenges and lose whatever hair I have.
Yeah, we're all hair challenged at this point.
What's the premise? What's the premise for this approach?
Well, I think it's a new architecture. It's a fairly radical change. When it works, it's potentially going to be far better. You've just got much more bandwidth. All the networking overhead goes away, if potentially. But the software has to catch up with the hardware, and the hardware has to work reliably. And there's a lot of firmware. If there's any bugs in the silicon right now, then they've got to find all those, work those out. So it is a new computer architecture. It's something I've talked about a bit over the years because there's another variation of this, which is, so this is based on NVIDIA's proprietary NVLink technology. The industry as a whole is moving to something called CXL, which is a industry-wide standard, which was going to give everybody a similar kind of ability to build very large coherent memory systems. CXL is still in the standards phase. It's probably a year or two behind where NVIDIA are, and they're still trying to debug the standard. So this is, I think, the next generation of compute architecture. We're going to have extremely large single systems, and I call these petaliths, these sort of petabyte scale monoliths. And I've been talking about it for a little while as it's been sort of coming. And I think we're starting to see, okay, we've got the first system that looks like this and we're trying to debug it. So that's exciting. And we'll hear whatever the next generation is from Jensen in his keynote. And that's going to be, he's got to have something new and exciting to talk about. So, okay, this is now old hat. We're trying to make it work. What's the next big thing? So that's going to be, I think, the keynote.
Yeah. One thing I'd add, Alex, is typically, from an architecture perspective, what's happening is these are, even the existing GPUs, they have a lot of compute, like a lot of flops to be used. But when you train large models, you don't get 100% utilization. You get 100% GPU utilization, perhaps, but it doesn't mean that you're using all the compute that you have for model training. So even today, when you train, 200 billion parameter model and so on, achieving anywhere between 30 to 40 MFUs or, that's actually a good thing. But what that means is you're losing out on 60% of the available compute. The model flop utilization, which is the MFU, is in 30, 40 ranges. People have been tuning. I want to say there are a few labs that have cracked the 50, 60% barrier, but in vast majority of folks are still really low. And one of the biggest culprits is actually networking and network topologies. And this architecture sort of takes you in the realm of, well, I'm not going to be spending too much time in transferring gradients. I'm not going to take too much time in feeding the beast of the GPUs with data. All of that goes away. So theoretically, we should have a big boost in training, and ultimately the cost of, say, training 100 billion parameter model, which say is in the 10 million range, goes down to 2 or 3.
Yeah.
How far ahead?
So it's much more about getting the more efficient use of the hardware. Also, because what we're trying to do when we're networking it, there are some extra tricks you do where you maybe do extra work that you didn't really need to do if you had it, because you're trying to work independently, and there's a little bit of duplication that happens, and then you merge everything. So if we don't need to do the duplicate work, that saves some money. or save some CPU, so floating point cycles. And then if you don't have to wait for the network, that saves some time. So ultimately, these new systems should run more efficiently. But obviously, the first thing is they have to get them to work. So I think we'll probably, in the keynotes, whatever, and some of the talks, will be, okay, how do we actually have it working yet? Do we have examples of people actually having it run? And there are people that have built supercomputers based on GH200 around the world, as well as AI training people, and they're going through the installation process and starting to do some first benchmarks on the basic one chip at a time level things. But the larger clusters, it's going to take a little while to get it going. So I think this is kind of one of those transition points, and the rest of the industry is going to have to figure out how to compete with this system and bring out something equivalent for themselves. But it looks like Nvidia is a year or two ahead of everybody in trying to get this working at scale. So that's kind of the teething pains, if you like.
How does this affect people who, are managing data centers or who are trying to think through how they build, application architectures or
If
people?
you've just spent a whole load of money buying a bunch of GPUs, they're probably going to be obsolete in a year. That's kind of what it happens. I mean, the biggest problem, I think, with buying on-premise GPU stuff is you can't. I mean, you now sort of um, you depreciate your CPU and your data centers over 3, 4, 5, 6 years. Right? A CPU is still a decent CPU 5 years later. The GPUs are kind of junk after 2 years, and they're not really that great after a year. So it's very hard to you have to kind of look at your depreciation curves and run them much faster for your GPUs. So that, I think, is a challenge for enterprises. And then the other problem they have is they just can't buy them, because you go to Nvidia and say, I want to buy 1,000
Yeah, you can't.
H100s, and they'll say, okay, we've got some in a year, or we've got some later this year or something. So there's a supply and demand mismatch, and it's probably exacerbated by people hoarding them if they can get them. And then a lot of workloads, basically the only place you can run them is in the cloud, because AWS and Azure and Google and a few others have already placed the big orders, and they're trying to have efficient sharing of the resources that they've got. So that's where you can run a workload. It may not be the cheapest place ultimately, but you can't physically get the system you need to run it in a data center for a while. So that's kind of I think the current sort of problems that if you're an enterprise trying to deploy a large scale training and inference workload right now.
Sunil, is this kind of thing on your mind, or is this not really
Well,
relevant?
maybe
Yeah.
Neil should talk about how you do your training and what your
Yeah.
workload looks like, and we could maybe
Yeah.
transition into the Flip AI story at
Yeah,
this point.
sure. One thing I would say is the availability of GPUs has gotten slightly better ever so over the last few months. As somebody who does train large models, for us, it was important to, and also as a small startup, I should have my GPU poor hat on
Yeah.
for this conversation. So we've been sort of cloud agnostic as far as training has been. So we've leveraged both AWS and Google Cloud to do our training. We've used some other smaller clouds because when capacity, we got denied capacity by AWS and GCP, had to go elsewhere. We, as I said, we built our stack to be sort of cloud agnostic. We standardize on PyTorch as like our interface to be, have an abstraction at the data level. So what I mean by that is we train over 100 billion tokens of data. We have various training phases that we use to train our models. But we didn't want a certain model architecture or a certain framework or even a certain chip be held hostage to any of these, because it's such a fast-moving, fast-paced area that we didn't. Only thing that's constant is good data. So we obsessed over that. What that has meant is, as newer architectures, from a model perspective, to encoder decoders and decoder only, to adapter networks, like all of those have come up. We've been able to sort of adapt to these newer things, and abstract, like having PyTorch as or sort of like the code base in PyTorch is good interfaces into XLA devices, be it like a TPU, be it the regular GPU, or even Trainium. We've been able to sort of use any of those to actually switch over. All truth being said, it's much easier to train with GPUs. Nvidia is still the king. I did try to sort of see if the king could be displaced, but so far the rest of them are failing. What Nvidia, it just works, right? Like it just works out of the box. You switch things, your code base just works. It doesn't fail, and I think and it's well understood, right? Like it's a matter of how mature the ecosystem is when it comes to training on NVIDIA. That has allowed us to sort of do that. I'd love to dive deep, but maybe Adrian, you have certain further probing questions in mind.
No, I think that makes sense. I think be interesting to talk a little bit about the difference between training sort of one big model, like the sort of monolithic ChatGPT thing, and the kind of mixture of experts models, and then your system of intelligent agents that you're doing, which is sort of a refinement. So let's try and sort of understand the architecture difference there.
Yeah, cool. I think what we find is there, even when you train a really large model, depending upon sort of the task that you do, it's not that all the neurons sort of participate in your inference path. There's always these sub networks that emerge, and that's been sort of the intuition behind building these mixture of experts over time. There's been like switch transformer early on papers from Google 3 or 4 years ago. There's a lottery ticket hypothesis, basically on the paths chosen. So they've been good fundamental research done on what part of the network or the entire model is being utilized.
So this is like, rather than having one person that knows everything, correct, you have a bunch of specialized people that each know a piece of the problem, and you have to build ways that they can talk to each other. So that's sort of the human network. We have a team solving your problem where you've got different expertise. So what you're trying to do now is instead of trying to train an AI model that knows all the things, you can specialize it to know the individual things. And then the problem becomes, what are those interfaces?
Correct.
And how can you track all that? So that's kind of what the mixture of experts sort of architecture looks like.
Is that the concept of AI? Is that the concept of the agents then?
I'll come to that and my interpretation of that. But to extend like what Adrian sort of saying, because of these individual decomposition, you're now actually able to steer them better. So what that means is if you want to influence a certain capability of a model, it's much easier than getting this one person who knows all the things there. Now, to Alex, to your point of agents, the way agents are sort of being labeled today is just this autonomous layer that allows you to do some task automatically, like, booking a ticket. So you can actually like tell your AI agent, hey, I want to book a ticket. I want you to
just kind of interject there. So basically, I think that the core difference here is that if it's a conversation like the sort of generative AI LLM model, ChatGPT, you type something in, you wait for the response, you type something in. That's a conversational system. But an agent is something that's more looking continuously. It's not a one-shot reply
Right.
response. It's just watching something continuously and trying to make sense of it and trying to update its model of the world. So it's a continuous data feed going in, and it's continually updating its view of the world or its stuff. So I think it's sort of not quite exactly real time, but it's more like this continuous reasoning. And I think this is sort of the difference between sort of the chat GPT world and maybe the autonomous car world, right? If you had to have a conversation with your Tesla to tell it to go around a corner and it didn't do anything while it thought about it, you'd crash, right? So it's the sort of thing that Tesla FSD is doing is an autonomous agent model. And I think what we're looking at here is bringing that kind of model to monitoring systems, and that's kind of where Flip comes in. This idea that you're monitoring continuously. So that's where I'd say mixture of experts is more chatting, and intelligent agents is more continuous.
Yeah, I think maybe I'll give a little background how we arrived at mixture of experts. So one of the things about observability data is it's multimodal, where multimodal in the sense like logs have its own language. You've got time series data and metrics and Prometheus. You've got traces, which are basically graph data. All of these different modalities have to come together. And that's one part of it. The other sort of part, if you sort of take different domains, like databases are a different beast, caching is different beast, different architectural patterns, and typically, and what I like to say is we are sort of modeling the war room as when it comes to actually debugging production incidents, right? Like you get on a war room call, you've got your DBA expert, you've got your networking expert. You got your caching expert and service owners, and everybody's coming together in terms of trying to best, suss out like, hey, is it my service or is it a combination of things that are happening? So that's what, eventually, both experimentally and semantically, this made a lot of sense where we saw trading a single model to do both time series data and code and log wasn't working well as theoretically it should. So, even though they both are sequence data, but the interpretation of the data is very different because in a code, there's all these contexts that you have previously, all of them come together, but in a time series data, they are sort of related, but it doesn't mean that the previous data point actually influences the next data point to an extent like code. So we had to develop a specialized sort of expert that could understand time series data. And that gave us a lot of boost in terms of our accuracy overall. So overall, I would say like it's more about modeling or mimicking things we find in the real world to be effective, which is, it's not usually one person who debugs the incident. It's a team that comes together, and we see that working well.
Well, why don't we take a look?
Yeah. So this is the Flip web interface. So this is where the debugged incidents come. What typically happens is Flip will hook into your observability system. We take read-only access into, say, a Splunk, a Datadog, a Dynatrace, CloudWatch, etc. And every time there's an alert that comes in through CloudWatch or PagerDuty or Jira ticket, we trigger the Flip analysis to debug what went wrong. In this case, there was a ticket that comes in where we have the error saying, hey, there's 5xx errors that have spiked. And what Flip does at this point is it generates a playbook on the fly given the issue at hand. So it sort of developed a skeleton of, hey, here are the 10 steps that I think I need to take. And at each step, it collects the data and evidence and then steers the next step based on the observation. So to Adrian's earlier point, right, like it's sort of re-educating itself in terms of observations and steering toward the goal. In this case, the goal is, hey, I want to find the probable root cause for why errors are spiking up. So the first step is actually identifying what is the impact. So the Flip model generates a CloudWatch query in this case. So this is an application where data is being sent to multiple places, where traces are being sent to Datadog, the infrastructure logs to AWS, and the application log into Splunk. Uh, and typically a developer does have to look at these multiple places in order to debug. And so that, at each step, what Flip does is actually surfaces all the evidence that it is grounding its data on, or it's understanding and inference on. So once it identifies where and what kind of error is happening, it further dives deep in a recursive manner. So it surfaces a bunch of logs which it deems interesting, and it's able to say, hey, the errors are on these two URIs. And once it's identified that, it goes into Splunk and writes a Splunk query, just like a developer would do, to say, hey, what are the errors that are happening? And in this case, it's interesting. You would see these are the unique errors that are happening. And Flip is able to say, hey, this seems like a network issue, or it has some hypothesis, right? Like network issue or the server itself. And it dives deeper. And as you can see, it sort of finds out that a connection pool errors, I don't find any error here that sort of supports my hypothesis. But wait a minute, I probably need to check the network layer. And lo and behold, it sees a bunch of things happening in the Kubernetes audit logs, but these are dialing events, which basically indicates, your DNS at the Kubernetes level is a little funky. And the model is able to say, hey, your latency goes from microsecond to millisecond range. Obviously, there is something wrong in terms of your network. It looks like network jitter is the reason why you're having these intermittent 5xx errors. And in this case,
so does this alleviate the concern I've heard with people about using AI tools in DevOps, that you have to be able to verify stuff? Is this a verification?
Absolutely. So we've been, I've been building machine learning systems for 15 plus years. Machine learning is never 100%. And Gen AI is far from it. So you have to instill trust in users, and you have to work through processes that allow you to be as close to 100% or trustable as possible. So we've done extensive work to ground our models and their interpretation in facts. So we look at the observed data. This is the reality. This is what has happened and measured by the system. And we want the user to have access to all the data that, support our interpretation. And I think so far, our customers love this approach, because in the odd case that, the responses or our summaries are not spot on, maybe they're there or thereabouts, the data is still available to our customers and developers. So in essence, we've eliminated 80-90% of the work that needs to be done, even when we're, say, slightly, off.
They're trying to write those Splunk queries correctly on the fly for a specific problem is the sort of thing. Well, hopefully you can write a Splunk query better than I can for a specific problem, right?
Yeah, thanks to our model.
That CloudWatch query was a bunch of gibberish, basically. But if you squint at it and you know what you're doing, you say, "Yeah, that looks about right." So we're assuming that you've figured out how to write those queries correctly, which is, it's AI, but it's something that's very well documented how to do that. And I think AI tends to work really well where it's something is extremely well documented. It's got a good syntax and structure, and particularly data analysis queries is sort of the sweet spot for sort of solving problems with AI, is what I've seen in terms of generating code. So we're generating the code to do the queries. and then surfacing the results so you can look at it and see if it makes sense. So I think the idea here is that this would save you a lot of time to get to this point where it says, okay, we've got some kind of networking problem. We can go and look at maybe what caused that, rather than trying to sort of go and gather all this information up front.
Yeah, I forgot to sort of show this entire debugging actually took way shorter than I took to explain. It only took 49 seconds for this entire report to be generated. And that's actually fundamentally different. Like, it's a shift in how DevOps and developers handle production incidents, because you're not starting with a ticket anymore. You're actually starting with an analysis report, which is a big shift in how think about incident debugging.
Aren't we seeing more examples of developers being able to solve these problems earlier in the process too? For example, I interviewed the founders of Atomic Jar and the test container technology.
Yeah.
And they solve a lot of the debugging issues way up front because you're able to debug as you go.
I would say there are two aspects. Like, there's a whole notion of shift left in terms of catching, static bugs and just regular, you write your unit tests, and things have gotten better with technology. But there's a whole different set of errors that only when the rubber meets the road in terms of, be it production systems, be it the scale at which the user behavior aspects, those things are almost sort of untestable in your lab. You always have to have the rubber meet the road, and while you can do all the things you can to sort of shift left, these class of problems are very hard, and I think solving that fast is a necessity, and I don't see that going away anytime soon.
I think think of it as developer problems and operations
Yeah.
problems. Like, if your
But
DNS
that's DevOps,
service
right?
gets flaky, that's something most developers, like, I have a name, it should turn into a machine that I'm talking to. If that isn't happening, that's not something wrong with your code. I think there's an interesting place in between. If you've got some chaos engineering tool like Gremlin or a fault injection tool in some environment, and you've got Flip there as well, then you could actually induce a problem and make sure that Flip correctly tells you what is going on, to prove that you've got your mitigation and you've got your debug processes working. So, I mean, you obviously, random things go wrong and you're trying to figure it out, but you can also do this chaos engineering fault injection thing where you're saying, okay, I'm going to pretend that a zone's gone down on my cloud provider. What should happen? And does Flip tell you that happened? Or if I have a problem with one of the API calls I make out to some other service, like I buy my DNS service from somewhere, maybe that they've gone flaky, or Splunk has got a problem, or one of those kinds of things. So there's a bunch of dependencies you have in your infrastructure, and you want to be able to be resistant to those. So in terms of shifting left, there's a sort of more operational view of chaos engineering, but there's also this idea of continuous resilience, where in your developer pipeline, as you release a new version of a microservice or a container, you test that and you actually induce problems on that to make sure that when that container tries to talk to some service that isn't there or is responding slowly, that container doesn't just keel over. It gives you a sensible error message in some form. And that's part of the sort of developers adopting chaos engineering as part of the development pipeline. And then you have more operational versions of it. And Flip right now is more focused on that operational side of, okay, I've got this thing in production, something weird happened. Where do I gather all the information to figure it out?
Maybe you could talk a little bit in conclusion, what is the foundation for the technology itself? I'd be curious about that.
Yeah. I'll start backwards in terms of, given we talked about chaos engineering. That's actually the icing on the cake, I like to say. We embrace chaos engineering to get the model ready for production. So once a trained model exists. We have we call it a chaos gym. So we have a setup where we bring arbitrary applications from GitHub. We provision them in EKS, ECS, GKE, all sorts, and we can instrument them with all of the popular providers. And we have a chaos LLM that is able to inject errors at different stages. So it can inject at the infrastructure layer. So we can use something like a fault injection service to get issues, inject chaos at the layer, AWS layer. And the next is the orchestration layer. We're able to inject errors in Kubernetes plane, right? So there are a bunch of tools. And then we have at the application layer, we can be as creative as developers to inject bugs, memory leak, and so on. So all of these combined, we are able to generate a lot of data. Again, this may sound to be, this is slightly different than synthetic data because it's closer to real applications, breaking in real ways and collecting. Although the process is synthetic, this allows us to get a lot of real world data and battle tested to be efficient when we go and deploy in a customer environment. As we all probably have experienced, you could be the smartest person out of college, but you still would probably fail to debug a production incident because you need to have those battle scars. And this is sort of like getting as battle ready as possible. That's my sort of analogy.
Reducing the time to battle readiness is a metric we all know, right? So just in conclusion, Sunil, what would you be curious about if you were going to the Nvidia GTC show? What would you be for your own technology purposes, your own interests?
I think the developer stack needs to be simpler. From Nvidia, I sort of joke around like, the stock's like, to the moon these days, but the developer pains still remain back at earth. So I think just helping the developer ecosystem better in terms of tooling, in terms of interoperability, across when you go across chips and so on. I think, if you said, hey, what's the magic wand, sort of action, if the GH200s become operational without bugs and so on, I'd be super happy because I'm going to be able to train models faster, cheaper, better.
Yeah, and it should be less complex to not have the networking overhead, and all of the sequencing that happens. So in theory, but it's just got a different set of complexities to optimize for. I'm going to be spending a lot of time in the expo looking at the vendors, trying to find vendors that are doing sort of monitoring, observability, performance, and developer experience kind of thing. So that's my kind of focus as I go around the exhibit hall.
Well, Adrian, thank you for joining us again today as co-host. It's great to have you here and look forward to your coverage from GTC. And Sunil, thanks for your insights and showing us a little bit about Flip AI. And to the little one back there, thanks for joining in. We've enjoyed your insights, so to speak. We look forward to the show for your coverage here, Adrian, for the News Stack. And Sunil, thank you so much, and we'll talk soon.
Wonderful, my pleasure. Thank you.
Yeah, thanks. Good to see you again.
If you like this video, please give us a thumbs up. And if you'd like to see more videos like this, you can always subscribe to our YouTube channel. We're on all the major social media platforms. You can always find us at thenewstack.io. We hope to see you soon.